So group homomorphism from one group G to another group H is a function from G to H such that f of A times B is f of A times f of B for all A, B in G. Notice there are two dots in this equation, but they're different dots. This dot is the multiplication of G, whereas this dot is the multiplication of H. Okay. And a one-to-one onto homomorphism is called an isomorphism. Isomorphism. And we say that two groups G and H are isomorphic. This is how we write in notation. If there is an isomorphism from G to H. So these are the new words. Okay. And I want to give examples. Plenty of them. So we only have the most trivial kind of examples. The identity function, the function that takes A to A for all A in G, that's an isomorphism from G to G. And the second thing, which is very important, is if you have two homomorphisms, then their composition is again a homomorphism. So if you have a homomorphism from G to H and a homomorphism from H to K, then you can apply them back to back. First F, then G, and this guy would also be a homomorphism from G to K. And in fact, if both of them are isomorphisms, then the composition is also isomorphism. But that's just a set theoretic fact. So I'll just say respectively isomorphism, then these words, homomorphism, isomorphism, are too long, so I'm abbreviating. Okay. There are more trivial kind of examples. These are very canonical examples. I think that's the more correct word. But they're not unimportant. They're like super important, the canonical ones, but they're sort of the ones that are automatic. I mean, if you have talked about isomorphisms of vector spaces, you have also seen these examples, is what I mean. Then there is the zero homomorphism, which is very far from being one-to-one and onto, or the trivial homomorphism. What do I want to call it? Maybe T for trivial. This is the homomorphism that takes all group elements to the identity, called the trivial homomorphism. You can check, in each case you need to check the defining property, this one. Okay. And then 4, if you have a subgroup of a group, it's called G is a subgroup of H, then the inclusion map I from G to H. This is the map that takes an element G to G. The only difference with the identity is that G is presumably a proper subgroup. So this is just taking an element of G and identifying it in H, because G, after all, is a subset of H, is one-to-one, so injective homomorphism. But if G is a proper subgroup of H, then this is different from identity, then it is not onto. So the identity is one-to-one and onto. This is neither one-to-one nor onto, usually, if H is non-trivial. This one is one-to-one but not onto. And then the first non-trivial example we'll see is onto but not one-to-one. So we have this standard map pi from Z to Z mod n defined by pi of k being the image of k in Z mod n, sometimes written k mod n. Verify that this is a surjective homomorphism. What does that say? That just says that pi of k plus m is pi of k plus pi of m for all km in Z. Right? The dot here is denoted by a plus. Both in Z and Z mod n, the group operations are plus. So that's what this equation reads. But this is just saying that the class of k plus m is same as the class of k plus the class of m. But that we know is true. This is basically how the plus is defined on this set. So I'm saying that the plus operation on Z mod n is defined to make this map a homomorphism. Okay. Indeed, if you take like Z mod 7 or something, then 5 plus 6 is the class of 5 plus 6. What is the right hand side? The right hand side is 11, which is same as 4. And indeed, the class 5 plus 6 is the class of 4. So this one is not one-to-one because the domain set is infinite, the codomain is finite, so there is no way to give a one-to-one map, but it's certainly onto. Okay. Here's an exercise. Verify that all non-zero homomorphisms from rational numbers to rational numbers are of the form. So I'm not just telling you some homomorphisms, I'm telling you all of them. F of A equals C times A for some C in Q. So just multiplication by a fixed number. So like if A equals 3/2 of A, that's a homomorphism. And all homomorphisms looks like this for some number. For example, we know these special maps, exponential map, that's a homomorphism from R with addition to non-zero numbers positive with multiplication. Or even, let's take non-zero numbers. So this is the map that's defined by x of A means e to the power A. What does this homomorphism property say? It says that x of A plus B is x of A times x of B for all A, B in real numbers. Notice both sides, the group elements are real numbers. On the right hand side only the non-zero ones. But the group operations are different. On the left hand side the group operation is called plus. So this dot in the equation defining a homomorphism on the left hand side, this dot is plus. Whereas the other dot on the right hand side is really the multiplication. It's the group law of the right hand side group. So this equation is what this equation is the instance of that equation in our example. This equation says that this exponential map is a group homomorphism. So e to the A plus B is e to the a times e to the b. Or for example, you have a fancier one. Let's call this E. This one goes from R to this circle group that we define. This is all complex numbers of absolute value 1. Looks like the circle, the unit circle in the complex plane. You have a map. E of A is a to the power I times A. It takes, or let's even write 2 pi IA. It's better. So what it does is it takes this, if you picture this, takes this line, here is real numbers, the domain, 0, 2 pi, 4 pi, etc. And it maps each of these intervals onto the circle. So if you start here and move right, you'll start going around the circle. And when you reach 2 pi, you have made one full circle. And when you go from 2 pi to 4 pi, you again go around in a circle. So as you keep walking on this line, you keep going around in this circle. It keeps on wrapping around this circle anti-clockwise. And if you go left, then it keeps wrapping clockwise. So this is the map E. This is a very, very important group homomorphism. And again, the group law just says, the homomorphism property just says that EA plus B is E of A, E of B. But on the right-hand side, it's the multiplication of complex numbers. On the left-hand side, it's the addition of real numbers. And another example, I lost count. This was 7. Oops. The determinant map. This is something that you have seen. From n by n real matrices to non-zero real numbers. This is a group homomorphism. In this case, the homomorphism property says determinant of a product of two matrices is the product of the determinants, which you know. Again, here, this product is the product of matrix, is the matrix product, whereas this product is the product of real numbers. Here's another example. Right, so let's take G to be our Z2. So these are, let's write them as column vectors. Then, here's exercise. Show that the homomorphisms from G to G are all of the form f of AB equals PA plus QB RA plus SB for some 2 by 2 matrix PQ RS. 2 by 2 matrix with entries in Z. So it's all given by some matrix multiplication. We'll see plenty of other examples in a little bit, but for a beginning, I think this is a varied enough list. And once you get a few, if you can compose them, then you get new ones again. So next time we'll start studying properties of homomorphism, start looking at kernels and images, and so on. See how it links up the two sides of the domain and the codomain.